Oh, hello. So, this is Klauss Dimitri, and I know that we're at the end of the semester and all this coronavirus stuff is going on, and I know you asked us to send our PowerPoint presentations, but I don't think my like PowerPoint presentations do itself justice by just sending them in. So I decided that I would record myself giving my PowerPoint presentation and upload it to YouTube and then just send you guys the link. So my PowerPoint presentation is on Blackbody radiation experiment, and it's about the confirmation of the Stefan-Boltzmann law. So uh, moving on to my presentation. Uh, Electromagnetic radiation serves as a major tool for science to understand the physical world. Infrared radiation is a particular section of the electromagnetic spectrum that all matter radiates, as it has direct connection to temperature. Thus, obtaining a deeper understanding of infrared radiation can help us explain why particular techniques that incorporate the infrared spectrum are used to understand other phenomena in the physical world. So, electromagnetic radiation, it's provides you information from long distances. So, there are many different ways, many different types of electromagnetic radiation that we use on a daily basis. And stuff we don't use as often. So we use sight a lot. There's radio waves that we use daily. Things that we use a little less, uh, microwave background radiation, X-rays, the gamma rays in space. But today my topic is more focused on infrared. So that includes our skin is able to detect infrared radiation, certain degrees of infrared radiation. So it's my topic's also about how infrared radiation is uh, learning more about it and the rules that govern it will allow us to get a deeper understanding of the universe we live in. So infrared radiation, the concepts of the black body and infrared radiation have vast utility in the modern world and can be found in technologies that range from military to household stuff, and even research at the frontiers of science in astronomy and material science. This is because all matter emits electromagnetic radiation that is related to its absolute temperature, and as such provides a means to gather information on any object up to even astronomical distances. So this really began on Stefan Boltzmann what's it called law really started out with the blackbody. Studying blackbody radiation. So blackbody is an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. It can emit radiation. The radiation it absorbs uniformly in all directions. Essentially, it is a body that does not reflect any electromagnetic radiation. It instead absorbs and emits it back out uniformly. An important concept to understand in order to fully grasp infrared radiation is this idea of the black body. And it's theoretically interesting because the radiation properties of a black body are independent of the particular material. So physicists can study the properties of intensity versus wavelength at fixed temperatures, which is really important for understanding our world. Yeah, so that's one of the big things about blackbody and why it's been so interesting, and it leads towards the development of the Stefan-Boltzmann law. So my idea in this presentation is to show you an experiment that can be done to prove that the Stefan-Boltzmann law is valid, and the quest for understanding black bodies provided us with this relationship. It's also important to know that we can prove it with not so complicated experiment. So this is the Stefan-Boltzmann law. I'll show you more about it as we move on throughout my presentation. So let's start out with this like the introduction backstory of the black body. So the whole concept of a black body began with Balfour Stewart in 1858, and he concluded that he did a few experiments on his own, nothing too intense. They were on absorptivity and thermal radiative emissive powers of different surfaces. And Stewart concluded that from his experience that the lamp black color possessed the greatest absorbing and emitting power. However, his mathematical and theoretical explanations were not rigorously valid. He failed to include thermodynamics in his paper, and he failed to address the relationship between power, emittance, and temperature, which is a core tenet of the Stefan-Boltzmann law. So moving on, and someone who was unaware of Stewart's work, the guy that I was previously talking about, Gustav Kirchhoff, performed his own experiments and addressed the relationship between emittance and temperature, and speculated on the idea of an ideal black body, whereas the previous guy only talked about a color and being like, oh, this is the most thermally emissive, absorptive and emissive material that there is, or color that there is. He actually speculated there was something that could absorb everything and emit everything that it absorbed, which would be a black body. So moving off and building off of Kirchhoff's work, Joseph Stalin made a really breakthrough discovery when he concluded that the proportionality between temperature and radiance, or power, radiance power, was to the fourth power, which is a pretty crazy idea to really even think of, because like normally you would think things are you don't think of many things that are to the fourth power, but the Stefan-Boltzmann law is one of those phenomena that you see as distance grows. You see the difference between, or the proportion between temperature and power is to the fourth power. So finally, Stefan-Boltzmann, this Stefan-Boltzmann law as it is known now, was derived by Ludwig Boltzmann from theoretical considerations and ultimately providing the mathematical dependence between the temperature of the body and the radiative power, as well as the emissive parameters necessary to conclude his and like make his law the simple state it is nowadays, and as we know it nowadays. So moving on, the Stefan-Boltzmann law is a crucial theoretical concept that is built into many of today's modern technologies. The development of modern-day electronics use these concepts to make sure crucial components don't overheat, like CPUs. Heat sinks are built using these concepts of the Stefan-Boltzmann law, and many other things that we use daily utilize this law. Like engineers needed to calculate many things to make sure things would work the way they do and things wouldn't overheat, or things along those lines. So the experiment that I'm going to propose today is one that it's centered around the concept of the black body, which led physicists to develop the Stefan-Boltzmann law. So here I'm going to describe an in-depth theoretical walkthrough and the necessary experimental setup in order to validate the Stefan-Boltzmann law. I will begin by summarizing the theoretical expectations and presenting any appropriate derivations, as well as going step by step in determining any necessary error propagations. So here's like the experimental procedure that or setup that we would do in order to be able to verify the Stefan-Boltzmann law. So you would need an ammeter, ammeter, a voltmeter, a power supply to power them, a radiometer, which would measure the admittance power coming from a source, and finally the source, which is here I'm calling it a Stefan Boltzmann source, but in this case it's a flashlight. It could be like a tungsten flashlight, tungsten filament flash light bulb, or anything along those lines that emits power and you can control it very well. And it's not a risk of burning if you change the current very much, which tungsten would be a good filament for that. So these are multiple instruments necessary to conduct such an experiment. And the experiment would begin by turning on like the radiometer and setting it, so that it's not like that in this case, but setting that it's 10 centimeters away from the filament in the Stefan Boltzmann source, and it faces directly at the filament on like a flat, stable support. And you need to make sure this is calibrated. I know these tools are very like sensitive and they can change very much, but calibration is important throughout the whole experiment. But you gotta also make sure that the temperature of the room is recorded and stuff, and from that you're gonna try to record two separate sets of data. So like you would record, you do kind of two mini experiments, I would say. So first you would incrementally turn up the source with the ammeter. You would increase the amount of current going through it by a particular amount every time, and you would read the values from the radiometer and record them. You would record both the ammeter, voltmeter, and the power that was output. A secondary experiment would be you keep the voltage and current the same, but now you're going to change the distance. So you would start maybe at 10 centimeters and do 5 centimeter increments where you push the light bulb source 5 centimeters away each recording. So these are two different experiments you could conduct that would provide you a good relationship between the voltage or power, and then you could calculate temperature by, well, I'll show you later the theoretical methods how you calculate temperature. Alright, so moving on, you could from this you could plot the power against temperature and see that it has a fourth power relationship. Okay, so moving on, let's start out with these equations, which are the main equations that we're going to use to determine the temperature and how it's associated to the power. So we recorded power, recorded voltage, and we recorded current. So you would be able to get resistivity from the current and voltage, and this relation will tie resistivity to temperature, and where voltage is directly proportional. So basically in this equation, this equation, this is Ohm's law, but this equation would be where T naught is the temperature of the room where the experiment was conducted. R naught would be the resistivity recorded at that room temperature. So like, what was the resistivity when at the room temperature? And this alpha is a constant that is equal to 0.0045 1 over k. So that's just a constant that exists. So moving on, now an enormous aspect of these experiments too, because you would be going back actually. So from this you would be able to get everything you need. You would have gotten the power from the radiometer, so you would know power, and you would know the temperature because you had gone through this calculation process. and then you would be able to plot the two, and the relationship, if the relationship's a fourth power relationship, then you would know that the Stefan-Boltzmann law is valid, you know. And there would be a constant of proportionality as well, but the important part is seeing that the fourth to the fourth power, and that between power and temperature is the proportionality between the two. So also another important aspect of all experiments is knowing what the error and error propagation is. So the theoretical derivation of, so yeah, you know, an enormous aspect of these experiments is the need to address the error of propagation and uncertainties that present themselves within these experiments. So to begin, the uncertainties associated with the current voltage and power measurements will be determined using standard deviation equation, where sigma x is the standard deviation, n is the total number of data points, and x bar is the mean. So moving on to the next step, the next equation you would need to determine the uncertainties associated with both temperature and resistivity is it's possible to determine the uncertainty of a function by using the partial derivative of the variables of that particular function as shown by the relationship here. Thus, by using this equation, it is possible to determine the uncertainty of R by establishing the relation of the partial derivatives with Ohm's law. So this gives us the process from which you can derive the proper uncertainty associated with resistivity. It is necessary to find the uncertainty associated with resistivity because we use resistivity to determine temperature, which I'll go on to explain next. So let me just make sure you guys know. So this is an established way to determine uncertainties from functions. So by applying Ohm's law that we were given, that gave you as V equals IR, and this equation, you can find you can apply it to get this equation, and from that you can manipulate it to just with some algebraic manipulation. I mean, taking the partial derivatives here and then some algebraic manipulation, you can get to this result, which is a simpler result that we desire. And from this equation we provided earlier, we can rearrange it in order to get a relationship that we can manipulate to get the uncertainty associated with temperature, which is this bottom equation. So I gave you this earlier. It was the one I was telling you about alpha, T naught, which is the room temperature, resistivity at room temperature, and you can manipulate so that this just makes it simpler, so that you have T on one side, temperature, which we're looking for, and also we needed to find the uncertainty for resistivity, because you know resistivity in the way we're going about finding temperature, we go through resistivity. So it's important to also find the uncertainty of resistivity because that will affect the uncertainty of temperature. So now we're going to find the uncertainty of temperature using this equation that we just had earlier, this one, and that uncertainty equation, putting those two together like we did for the Ohm's equation and the same thing, we can manipulate it so we get delta T, and sigma T, and with some algebraic manipulation we can get this more simplified equation that provides us with the uncertainty of T, of temperature. And now we really have all the necessary information required to properly conduct this experiment and provide a meaningful result with an associated error. So this gives us all the tools we will need to prove the Stefan-Boltzmann law. We just plot power and temperature against each other. See that if it's to the fourth power, and we'd also apply our uncertainties that I showed you how to get. So I appreciate everything. Here are my references that I used to get through the theory part and see some of the previous experiments done in the past. And thank you very much for everything. And I hope you enjoyed that. I know I stutter a lot, so thank you very much for listening.